We will now study interpolating polynomials, and a particular form is chosen, the one called a Newton form. Let's just revise what the problem is about. We are imagined that we have some unknown function f, and we are given n sample points of this function, x1, x2, x3, xn, and the corresponding function value at those x positions. So the x sample points and the values of x are known data for our problem. We really don't know f. However, we wish to find a polynomial p of x such that this polynomial will interpolate the known sample values. And of course, we hope this polynomial would be a good representation or good approximation to this unknown f function. So remember that right now we are thinking of our problem as we know f, but in a real setting f is actually unknown. So before we will move on to talk about what a Newton polynomial is, we will try and create a programming framework that would provide us with a problem we can play around with. So let's open up Maple. And I like to have a few cells to work with here, so I'll just create some stuff. So it's always a good idea to do a restart in Maple, so we can ensure that we have no side effects. And I'm thinking I want to use the data structures and stuff from the linear algebra package, so I will just include this right here for convenience. And I use this colon thing so I don't get a lot of output. To play around with interpolation, it would be interesting to have some very nonlinear data to work with, so we better can see how good our interpolations are. It would be an advantage to have something that's nonlinear. So let's create some fancy function. I'll use the symbolic language for this. So an exponential is something that's very nonlinear. Sinus curve is also nonlinear. So this would probably give us something interesting to look at. Let's try and plot this. I'm actually storing the plot in a variable f, which allows me later on to make other plots and be able to show the plots on top of each other. That would make it more convenient for me to compare my interpolating solution with the ground truth. This is actually what I'm gonna plot now. Let's see, I wanna plot it from the interval -10 to, to 10, something like this. And we don't wanna see all this output. Okay, let's see how that works. Actually, I won't like to see this. Okay, so we see we get something that's kind of oscillating a little bit, going down and up. So this is something that's really not a polynomial. So it would be interesting to do polynomial interpolation on this to see if we can recreate this function using our polynomial in place of the function. Okay, so I need to create the sample points now. So I want some x values, and I'm gonna exploit the random vector function from the linear algebra module, or package as it's called in Maple. And let's make this one. Let's just create n, which is the number of sample points. Let's just call it 4 right now. We can go back and change it later when we are done with our implementation. And I need to give a parameter here, a shape parameter, that's gonna say something about where I'm gonna sample these x values. And let's see, something interesting happens around, I guess around 3 to 10. So we'll just pick our values in this interval like this. Let's just see if that works. we made an error here. Let's just go through and see what went wrong. So the error is actually not really an error, it's because I forgot to evaluate this cell up here, which means n was unknown when I tried to write this code. Now I've evaluated the cell before, so when I write, or if I evaluate this cell now, it knows what n is, and we can see that we get 4 sampled x values along this one. And if we go up here and change this to, let's say, 7, reevaluate this one, we see we get 7 values. That's nice. I really don't want to see these values, so we'll just do like this. Then we need the corresponding f values as input for our interpolation problem. So I would like to use the symbolic expression for my f function to get the f values. So that suggests I should do a map, and I want to map my x values onto the function f expression. However, I cannot write this as I have done right here. I need to change this symbolic expression into something that Mabel can use for its programming language part. So it's the unapply command I want to use, and I want to turn the x symbol up here into an argument that can be used by the map function, so it can take each of the values in x values and apply those to the argument. So it should be something like this. Let's see how that works. That looks nice, seems right. And we'll just remove the output here. Okay, so let's plot the sample points on top of the known function, so we can see where they are lying. So we want to draw this as points, style points, and we want to change the color. Let's use blue, something like this. Let's see, did something wrong. Okay, this has to be points, I think. Okay, that looks better. And to show them on top of that, we're going to use another package called plots. Just going to pull that one in, and then we can use the display method from the plots package. We just give the plots as a set, like this, I think. Let's see if it works. And here we see our red ground truth function, the one we actually want to reconstruct through this interpolation idea, and we can see the blue sample points on top of the red function. So this is the problem statement, our input for our Newton interpolation. Okay, so let's go back to look at the Newton form of these interpolating polynomials. So I just written it up here, took this directly from the textbook. I changed the notation a little bit here because the textbook uses zero indexing when it writes up all the math theorems, but in Mabel, all data structures, they are naturally used in one-based indexing. So I changed I running from I equals 0 to I equals 1 and added a +1 up here instead. These coefficients are given by divided differences, and we'll see in a minute how to compute these. And this is a product of x differences, so it's the x value which to evaluate our polynomial at, and the known sample x values here. So this is given from the textbook. This is what we need to implement. Now let's look at the divided differences, how to compute those, and then afterwards we will look at how to compute this whole summation here and this product terms of these things. So divided differences are defined as follows. So the divided difference of fxi is basically just the function value at xi, and if we look at the divided difference of xi up to xi plus j, it is given by this recursive definition. So you see, here we are also using a divided difference, which you basically get from removing the xi here, put that in here, minus a divided difference that you get from removing the right-hand endpoint, and then you divide by the x difference between xi plus j minus xi. So this is given by definition. Let's try and look at how to use this definition to actually compute divided differences. And for that, we will write up a little table here. We will call this our divided difference table. Initially, we start out just filling in the first column the actual function values that we know. So remember that f of 1 is actually just f of x1. So we just fill in that value here and simply for the next sample point here and here and here and so on. So okay, then we want to compute our first divided difference. So we will take the divided difference of f2 and f1. So we want to store this over here in the first column of the second column here, the empty one. So this one up here will be this value minus this value divided by x2 minus x1. So we can fill this in this value here. Okay, so this gives us the divided difference here. Next, we will compute the divided difference of f2 to 3. That means we take this value minus this value divided by x3 minus x2 and store it here. The same for the next one. So the divided difference of f3 to 4 is this value minus this value divided by x4 minus x3, and so and so. And here I just cheated and filled in all these values. You notice that the last one down here, the divided difference of f5 to f6 does not exist and nothing should be filled in here. This part of the table is basically just empty. Okay, now we have all the divided differences involving 2 sample points. So now we will take the divided differences involving 3 sample points. This will be stored in the third column of our table. So the first one we will attack is this one on top. So that would be divided difference of f1, 2, and 3, which is this value minus this value divided by the difference of x3 minus x1. Similar here, this would be the divided difference from f2, 3, 4 being this value minus this value divided by x4 minus x2, and so on and so. And this we will continue doing all the way through the table. And in the end, we have the divided difference including all the sample points, which would be this value minus this value divided by the difference between x5 and x1, and so on and so on. So as this already suggests, a convenient data structure for storing these divided differences could be a matrix. And let's see if we call that matrix C in Maple. We will see here how the divided differences would map into that matrix. So we see that the first column will just be the sample values. The second column would be all divided differences with 2 points involved. The third column would be all the divided differences with 3 points involved, and so and so. So by looking at how the matrix indices map to the indices in the finite differences, we can come up with a general rule for how to fill in any entry in this matrix. And here I just wrote it up. So entry I comma j in the matrix would be equal to divided difference from xi to xi plus j minus 1. Okay, so now we are ready for implementing a subroutine, a procedure that can compute the divided difference table. So let's go back into Maple. We are here now. So I will call this function divided differences, and it should, as input, take x values and f values. We're gonna need these, and we're also gonna need the evaluation point that we are looking at. So I'm gonna call this xx, because if I call it x, Maple will get confused because I used x as a symbol up here. Now I want to use it as an argument of parameters. So in order to be sure there are no side effects of things, I will just call this xx. Okay, and we need an end here. So it might be a good idea to know how many sample points we have. We're gonna do this, just counting the number of elements in the input here. And then we need a matrix for storing our computed values. So let's see, this should be n by n matrix, I guess. And probably also need some variables for iterating all the entries. So if you remember, the first thing we did in the table was to fill in the first column with the function value. So we will do that now. Something like this. And let's just see, that looks okay. Then we need to iterate over the columns. So we want to start with column number 2, because column number 1 we filled in with the function value. So we start by running down through the second column. And we have n columns in total. It's going to be like this. And in each column, we're going to iterate over the rows. We're going to start from the top. So that would be from first row. And then we have to go down. And we have to go down such that we only do the upper triangular part of this matrix. This would be, let's see, +1, I think. Okay. And then we take the rule that mapped entry I comma j. So this is the divided difference formula we are going to implement here. Oops, that was too fast. This, and here we need to take the values from the previous column, and it would be one row below minus the row before, like this. let me see, I think this is basically it. Then we want to return C, and I can see that we're actually not gonna need this XX here for evaluating the divided difference, so we just remove that one. It's not really needed. Okay, let's see if this works. Okay, Mabel accepted what I was writing. Let's just try and test if this gives something. I have to spell correctly, otherwise we just get strange errors. Okay, so let's see. We got our function values here, and it seems we got the right fill pattern. Okay. So now we have a sub routine implemented as a procedure in Mabel that can compute the divided differences that we need for our Newton polynomial. So let's go back to theory a little bit. So back to theory, we have the Newton form of an interpolating polynomial, and we just created a procedure that could compute the divided differences, meaning these coefficients going into the definition right here wherever you see a red circle. So now we need to write a procedure that can evaluate this summation over all these products. And in order to do so, it could be helpful just to write out all this for a small example. So let's try and do that. And I cheated and prepared it a little bit here. So this is just an example having 5 sample points. Otherwise it would not fit on a slide. So here I just wrote out the summation, and you see here the product terms in each row. So if we implemented this straightforwardly, we could have a for loop that evaluated the summation, and for each term in the summation we could have another for loop that evaluated the multiplications. But that would basically make our overall computational cost be n squared, which is a little bit unpleasant. That would be computational heavy to have if we have many sample points. So we're going to use a technique called nested multiplications to get this time complexity to be a little bit more nice. So when we look at this one here, we immediately notice that these 4 rows all have x minus x1 term multiplied on them. So the idea is now to take x minus x1 and factor that outside of these 4 lines. I've done this now. So you see x minus x1 is here. This would be the first line, or actually the second line, third, fourth, and fifth line. And if we look at what remains here, we see that x minus x2 is a common factor for the 3 lower lines. So we repeat with the trick here and factor out x minus x2. If we do this, we will get something that looks like this. And we see that the remaining 2 rows have x minus x3 as a common term, so we can factor that out, and so on. So this idea, if we write that into math notation, it goes as follows. The interpolating function would be given by this m1, which is just something I use to help me write up things. Vms is defined recursively like this, so mk would be equal to the coefficient c1k plus x minus xk times m of k plus 1, and you see this holds for all k from 1 to n minus 1. So when I have mn minus 1, it would use mn, which is not defined by this relation, but instead is defined by this criteria down here. So this is a recurrence relation that essentially do the same thing as I showed before with the nested multiplications. And this is something we can implement using a for loop, an iterative way to implement the recurrence equation, which means that the computational cost now of evaluating our Newton polynomial is linear. It scales as n in the number of sample points. So let's now try and implement this nested multiplication in our little Maple example. So we'll go over here and we need to create a procedure for it. So let's call this one Newton, and it needs the x values and it needs the f values like this, and this time I would need the evaluation point where we wish to know what the value of the function is. Okay, so one more time, it would be nice to know how many elements we are dealing with. So or how many sample points we're dealing with. So we're just gonna ask how many elements are in x values, and then we wish to get our divided differences, and here we're just gonna call the little help routine we created before, the subroutine. Like so. And let's see, what more do we need? Then we need to implement our nested multiplication, so we will make a local m. This is gonna be the subterms we're gonna create, and this has to be equal to c1n to start with. And then we need a for loop, so we need a counter. Let's call it k to have it look similar to the theory we outlined. So we're running for n-1 to 1 by -1. So if we go back and look at the theory, we can see here k. We are running backwards, computing from mn down to m1, and simply just adding up terms as we go along. And in the end, when we reach m1, we know what our polynomial is, and we can just basically return the value of m1 as the result. So let's go back here. We need an undo, and then we should update m using the recurrence relation that we found. So let's see, this would be xx minus x values of k times m plus ci comma ck, sorry, c1 comma k, like this. Let's just check the equations. c1k plus x minus xk times m. That seems right. Okay, and when we're done, we're gonna see just return value we computed as our result, like this. Okay, so let's see if Maple likes what I have written. At least it does not disagree so far. So now it will be interesting to see if the implementation is correct. I'm going to cheat a little bit. I'm going to exploit Maple's ability to mix symbolic language here with programming language, and I'm going to create an expression, symbolic expression, using this function. So the function I wrote up here is for number crushing. So it's kind of a fun thing to do. So we're gonna do like this. Gonna call Newton with our sample values and our function values, and then I'm just gonna say, hey, I'm gonna use my symbol x as the evaluation point. So when Maple substitute a symbol into this procedure up here, it will generate symbolic expressions when it runs, rather than creating function values or computation values. So that means this expression here should generate a polynomial for me, And we can just look, seems like that. Can recognize this nested multiplication method in this output. So now when I have this symbolic expression, I can actually plot it. So let's create a plot for it. And let's use the same interval as our first plot, like this. And we see something like this. And then we can try and put them on top of each other. So we're gonna do display of like this, and we should be able to see the whole thing like this. So looking at the end result of this curve, one may expect that we did something completely wrong. It seems like the solution goes off to something and all points are sort of like collapsed on the x-line, but it's basically just because that we are plotting far away, far outside where the sample point is, so the interpolating function really doesn't make sense out here. So we should be able to fix this by just changing the interval of where we draw the plot function to match or be more like the interval where we have sample points in. So let's just do that here and see what we get. Let's try one time. There we go. So now we actually see that we do find an interpolating function, the green one, a polynomial that goes through all our sample points. So let me just try and clean up my code a little bit by putting everything into one cell. That makes it a little bit easier for us to evaluate everything in one go. So here we have it, like this. Okay, let's just run through the example. We do restart, make sure we have linear algebra and plots packages so we can use them, create some fancy function, gonna plot it in some interval, let's say from 3 to 10. I'm gonna pick out some sample points here, just pick 20, it could be anything, I can play around with it. Gonna create some sample points, gonna plot the sample points, and just to display the initial problem that we're gonna solve, we're just gonna make a plot here. Then there's the divided difference function or procedure that we implemented, the Newton procedure we implemented. That's the line generating a symbolic expression for the interpolating Newton polynomial. And then we're gonna plot that interpolating polynomial, and then we hope to see everything on top of each other. So let's run it. And there we go, and we can compare the red to the green and see they're kind of similar. And now it gets fun because now we can simply just go in and say, hey, let's use n equal 4. And let's see what happens. So we notice that now the green and the red curves are very different, but the green curve is still interpolating the sample points we are given. It's simply just because there's too few sample points to capture this nonlinear behavior of the red curve. So if we increase the number of sample points, we should get a better result. Increase it a little bit more. There you go. So, end of story.